In the cold silence of space, something extraordinary happened. The James Webb Space Telescope, humanity's golden eye on the cosmos, slowly turned its gaze toward a very specific point in the southern sky. Not toward the distant galaxies it has become famous for revealing. Not toward the glowing nurseries where new stars are born. No, this time, Webb looked somewhere much closer to home. It looked toward our nearest stellar neighbors, the stars of Alpha Centauri. And what it found there has left scientists stunned, excited, and perhaps just a little bit unsettled. Before we float off into the stars together, I'd love it if you gave this video a like and maybe even subscribed if you haven't already. It really helps this sleepy little channel grow. Now, let me take you on a journey. A journey that begins with a question that has haunted humanity since we first looked up at the twinkling lights in the night sky. Are there other worlds out there, orbiting other stars? And if so, could any of them be anything like our own pale blue dot? These are the questions that drove astronomers to point the most powerful space telescope ever built toward Alpha Centauri. And the answers they found are changing everything we thought we knew about our cosmic neighborhood. Picture this. You are standing outside on a clear, dark night. The kind of night where the Milky Way stretches overhead like a river of light. If you happen to be in the southern hemisphere, perhaps in Australia or South Africa, or the southern tip of South America, you might notice a particularly bright star near a distinctive cross-shaped pattern of stars. That bright star is not actually a single star at all. It is the Alpha Centauri system, 3 stars bound together by gravity, dancing through space as cosmic companions, and they are the closest stars to our own sun. The Alpha Centauri system sits just over 4 light-years away from us. Now, 4 light-years might not sound like much when you hear it said quickly, but let's slow down for a moment and really think about what that distance means. A light-year is the distance that light travels in one single year, and light is fast. Incredibly, almost unimaginably fast. It zips through space at about 186,000 miles every single second. In the time it took you to read that last sentence, a beam of light traveled far enough to circle the entire Earth more than 7 times, in just 1 second. Now imagine that same beam of light traveling not for 1 second, but for an entire year. 365 days of racing through the void at that tremendous speed. At the end of that year, the light would have traveled about 6 trillion miles. That is a 6 followed by 12 zeros, a number so large it almost loses its meaning. And Alpha Centauri is more than 4 times that distance away. Roughly 25 trillion miles separate us from our nearest stellar neighbors. To put this in perspective, imagine you could drive a car to Alpha Centauri at highway speeds. Let's say you were traveling at 60 miles per hour day and night, never stopping for gas or rest. It would take you about 48 million years to get there. Or consider the Voyager 1 spacecraft, the fastest object humans have ever launched into the depths of space. Even Voyager, traveling at around 38,000 miles per hour, would need more than 70,000 years to reach Alpha Centauri if it were heading in that direction. So when we say Alpha Centauri is close, we mean close by cosmic standards. In the vast ocean of the Milky Way galaxy, which contains hundreds of billions of stars spread across 100,000 light-years, Alpha Centauri is practically next door. If our galaxy was shrunk down to the size of the continental United States, and our sun were a grain of sand in New York City, then Alpha Centauri would be another grain of sand just a few feet away. Meanwhile, the center of the galaxy would be somewhere around Kansas, and the far edge would stretch all the way to California. Our stellar neighborhood is tiny compared to the immensity of the galaxy, and yet even this tiny neighborhood contains worlds that have captivated human imagination for generations. The Alpha Centauri system is a cosmic family of 3 stars. The largest and brightest of the trio is Alpha Centauri A, also known by its traditional name Rigil Centaurus, which means the foot of the centaur in Arabic. This star is remarkably similar to our own Sun. It is a yellow star, just slightly larger and a bit brighter. If you could stand on a planet orbiting Alpha Centauri A and look up at your Sun, it would look very much like the Sun we see from Earth, a warm, golden disk of light. The kind of star that, according to everything we know about stellar physics, should be perfectly capable of hosting planets where life could flourish. Alpha Centauri. A has about 10% more mass than our Sun and shines with about 50% more light. Its surface temperature is nearly identical to the Sun's, around 5,800 degrees. It rotates once every 22 days or so, and it shows the same kind of magnetic activity that our Sun displays, with spots and flares and cycles of activity. In many ways, Alpha Centauri A is like looking into a cosmic mirror, a twin of our Sun, just a little older and a little brighter, sitting in a stellar system that formed from the same raw materials as our own, about 5 billion years ago. The second star in the system is Alpha Centauri B, also called Ptolemy. This star is a bit smaller and cooler than both our Sun and Alpha Centauri A. It glows with a more orange hue, containing about 90% of the Sun's mass and shining with only about half its brightness. Despite being smaller, Alpha Centauri B is still a perfectly respectable star, millions of times larger than Earth, burning hydrogen in its core and radiating warmth into the surrounding space. It orbits together with Alpha Centauri A in an elongated dance that takes about 80 years to complete one full circuit. These 2 stars, A and B, form what astronomers call a binary system. They are gravitationally locked together, orbiting around their common center of mass like 2 figure skaters holding hands and spinning around each other. Their closest approach. They come within about 11 astronomical units of each other, roughly the distance from our Sun to Saturn. At their farthest, they swing out to about 36 astronomical units apart, similar to the distance from the Sun to Pluto. This cosmic dance has been going on for billions of years and will continue for billions more. The third member of the family is the smallest and dimmest, but in many ways the most famous. Proxima Centauri, also known as Alpha Centauri C, is a tiny red dwarf star. It contains only about 12% of the Sun's mass and shines with less than 1% of the Sun's brightness. You could never see Proxima Centauri with your naked eye, even though it is the closest star to Earth beyond our own Sun. At 4.24 light-years away, it is actually slightly closer than Alpha Centauri A and B, which sit at 4.37 light-years. Proxima orbits the main pair at a tremendous distance, about 13,000 astronomical units away, taking more than 500,000 years to complete a single orbit around its larger companions. Now, here is where things get really interesting. Proxima Centauri has planets. We have known this since 2016, when astronomers announced the discovery of Proxima Centauri B, a world roughly the size of Earth orbiting in what scientists call the habitable zone. This is the region around a star where temperatures might be just right for liquid water to exist on a planet's surface. Not too hot, not too cold, but just right. The discovery sent waves of excitement through the scientific community. The closest star to our Sun had an Earth-sized planet in its habitable zone. It seemed almost too perfect to be true. But as astronomers studied Proxima Centauri more closely, complications emerged. You see, Proxima is what scientists call a flare star. It is prone to sudden, violent outbursts of energy that can increase its brightness by a factor of 10 or more in just a few minutes. These flares release torrents of radiation and charged particles that would wash over any nearby planet, like cosmic tsunamis. A planet orbiting as close as Proxima B does would be bombarded constantly by this harsh stellar weather. The numbers are sobering. Proxima B receives about 30 times more extreme ultraviolet radiation than Earth receives from our Sun. It also gets blasted with 250 times more X-rays. Over billions of years, this radiation could strip away any atmosphere the planet might have had, leaving it as a bare, sterile rock. Or perhaps the atmosphere could have survived if the planet has a strong magnetic field like Earth does, deflecting the worst of the stellar tantrums. We simply do not know yet. The question of whether Proxima B could support life remains one of the great mysteries of modern astronomy. Since that first discovery, astronomers have found evidence of at least one more planet orbiting Proxima Centauri, a smaller world called Proxima D that orbits even closer to the star. But the focus of our story today is not on Proxima Centauri. It is on the larger, brighter, more sun-like stars of the Alpha Centauri system. Because in August of 2024, the James Webb Space Telescope turned its powerful instruments toward Alpha Centauri A, and what it found there has the potential to reshape our understanding of planetary systems throughout the universe. To understand why this observation was so challenging and so significant, we need to talk about how astronomers actually look for planets around other stars. The problem is that stars are bright, incredibly, overwhelmingly bright. A star like Alpha Centauri A shines trillions of times brighter than any planet orbiting it. Trying to see a planet next to its parent star is like trying to spot a firefly hovering next to a lighthouse from miles away, while the lighthouse is shining directly in your eyes. Most of the nearly 6,000 exoplanets we have discovered so far were found using indirect methods. The most common is the transit method, where astronomers watch for tiny dips in a star's brightness that occur when a planet passes in front of it, blocking a small fraction of the starlight. Another popular technique is the radial velocity method, which detects the tiny wobble that a planet's gravity induces in its host star. These methods have been tremendously successful, revealing a cosmos teeming with worlds of all sizes and types. But there is another way to find planets, a more direct approach that astronomers have dreamed of for decades. What if you could actually see the planet itself? What if you could block out the blinding light of the star and photograph the planet directly, like taking a picture of that firefly after turning off the lighthouse? This is called direct imaging, and it is extraordinarily difficult. Only a handful of exoplanets have ever been photographed this way, and all of them have been large, hot, young planets orbiting far from their stars. Worlds that glow brightly in infrared light because they are still radiating the heat of their formation. This is where the James Webb Space Telescope comes in. Webb was designed with instruments that push the boundaries of what is possible in astronomical observation. One of these instruments is called MIRI, the mid-infrared instrument. MIRI can see light in the mid-infrared part of the spectrum, wavelengths that are invisible to our eyes, but carry crucial information about distant worlds. At these wavelengths, the contrast between a star and a planet is much more favorable than invisible light. A planet that might be trillions of times dimmer than its star in visible light might be only thousands of times dimmer in the mid-infrared. MIRI also has a special feature called a coronagraph. Think of a coronagraph as a tiny shield built into the telescope, designed to block out the light of a bright star so that astronomers can study the much fainter objects nearby. It is like holding up your thumb to block out the sun so you can see something in the sky near it. The coronagraphs on MIRI use sophisticated optical techniques to suppress the overwhelming glare of a star, potentially revealing planets, dust rings, and other structures that would otherwise be invisible. But observing Alpha Centauri with Webb's coronagraph presented unique challenges. For one thing, Alpha Centauri A and B are incredibly bright, so bright that the telescope's sensitive instruments could be overwhelmed if not handled carefully. The stars are also close together in the sky, meaning that blocking the light from one still leaves you dealing with scattered light from the other. And both stars move quickly across the sky compared to more distant objects, requiring the telescope to track them with unusual precision. The team of astronomers who planned this observation knew they were attempting something that had never been done before. They were going to try to directly image a planet in the habitable zone of a sun-like star, not a hot, young giant planet orbiting at a safe distance, but a smaller, cooler world tucked close to its star where liquid water might exist. If they succeeded, it would be the most important discovery in the history of exoplanet science. A world close enough that future telescopes might be able to study its atmosphere and search for signs of life. In August of 2024, the James Webb Space Telescope executed this challenging observation. The team used MIRI's coronagraph to block out the brilliant light of Alpha Centauri A, while carefully subtracting the scattered light from Alpha Centauri B. They processed the data using advanced techniques, looking for any faint point of light that might reveal the presence of a planet. And they found something. There, nestled in the data, was a faint blob of light, a tiny point source sitting at about twice the distance from Alpha Centauri A, as Earth sits from our Sun. The object was 10,000 times fainter than the star itself, exactly what you might expect from a planet. The team was cautious but excited. They knew that images like this can contain artifacts, false signals created by the telescope's optics or by the complex process of subtracting out the starlight. They tested their data rigorously, looking for any way to explain the signal as something other than a planet, but the signal remained. What they had potentially found was extraordinary. A gas giant planet, roughly the mass of Saturn, orbiting Alpha Centauri A. This would be the closest planet to Earth ever directly imaged around a sun-like star. A world in our cosmic backyard, just 4 light-years away. A planet that challenges everything we thought we knew about how worlds can form in the chaotic gravitational environment of a binary star system. But then something strange happened. When the team looked again at Alpha Centauri A in February of 2025, the planet was gone. They looked again in April. Still no sign of it. The mysterious object that had appeared so clearly in August had vanished without a trace. What happened? Where did the planet go? Had they imagined the whole thing? The scientists faced what they called the case of the disappearing planet. But rather than concluding that the original detection was a mistake, they did what good scientists always do. They ran the numbers. They created computer models simulating millions of possible orbits for the candidate planet. They asked a simple question. If a planet were really there, under what circumstances would it be visible in August, but invisible in February and April? The answer was surprisingly reassuring. In about half of the stable orbits they simulated, the planet would have moved too close to the star by early 2025 to be detected by Webb. The planet was not gone. It was just hiding, its position in its orbit temporarily carrying it too close to the star's glare for the telescope to pick out. This finding aligned beautifully with a puzzling observation from years earlier. Back in 2019, a different telescope had caught a tantalizing glimpse of something near Alpha Centauri A, but that observation could never be confirmed either. Now, with the Webb data, the pieces started to fit together. If the planet is real, and I want to be clear that it has not been confirmed yet, it would be orbiting Alpha Centauri A in an elliptical path. At its closest approach, it would be roughly the same distance from its star as Earth is from our Sun. At its farthest, it would swing out to about twice that distance. This elliptical orbit would carry the planet through the habitable zone of Alpha Centauri A, the region where a rocky planet might have liquid water on its surface. But here is a crucial detail. This candidate planet is not a rocky world like Earth. Based on its brightness in the infrared and the orbital calculations, astronomers believe it is a gas giant similar to Saturn, a planet made mostly of hydrogen and helium, with no solid surface to speak of. You could not land on this world any more than you could land on a cloud. It would be a beautiful place to visit, no doubt, with swirling bands of atmospheric patterns and perhaps rings of ice and dust encircling it. But it would not be a place where life as we know it could take hold. Does this mean the Alpha Centauri A system is a dead end in the search for habitable worlds? Not necessarily. Think about our own solar system. Saturn exists alongside Earth. Jupiter exists alongside Mars and Venus. Giant planets and small rocky worlds can coexist in the same system, each finding its own stable orbit around the central star. In fact, some astronomers believe that giant planets may actually help create conditions favorable for life by shielding inner planets from asteroid impacts and by influencing the delivery of water and organic molecules during the early history of a planetary system. However, there is a complication. The elliptical orbit of this candidate giant planet sweeps through most of Alpha Centauri A's habitable zone. This is concerning because a massive planet plowing through the habitable zone on a regular basis would gravitationally disturb any smaller rocky planets that might be trying to orbit there peacefully. It would be like having a cosmic bully stomping through the playground, knocking smaller kids off the swings every time it passed by. Astronomers believe it may be unlikely that smaller rocky planets could survive in stable orbits within the habitable zone of Alpha Centauri A if this giant planet exists. But let's not get too discouraged. There are still possibilities. Rocky worlds might exist in orbits closer to the star, where they would be safe from the giant planet's gravitational influence, even if they would be too hot for liquid water. Or perhaps smaller planets could exist in stable configurations further out, in cooler regions where water would be frozen rather than liquid. Or maybe, just maybe, moons orbiting the giant planet itself could harbor conditions suitable for life. Think about it. If this Saturn mass planet exists, it might have its own collection of moons, just like the real Saturn has Titan and Enceladus and dozens of others. Some of those moons could be large enough to hold atmospheres. Some might have internal heating from tidal forces, keeping subsurface oceans liquid even in the cold depths of space. We have learned from studying our own solar system that moons can be every bit as interesting as planets when it comes to the question of habitability. For now, the candidate planet around Alpha Centauri A remains unconfirmed. Astronomers need to observe the system again and again, waiting for the planet to swing back into view, verifying that the signal is real and consistent with the predicted orbit. If future observations with Webb or other telescopes can catch the planet again in a different position, that would strengthen the case enormously. And if the planet is confirmed, the next step would be to try to learn more about it. What is its atmosphere made of? Does it have rings or moons? How did it form in such a complicated gravitational environment? These are the questions that keep astronomers awake at night, their minds racing with possibilities. And these are the questions that drove them to look toward Alpha Centauri in the first place. Because Alpha Centauri is not just the nearest star system. It is a window into how planets form and evolve around stars that are similar to our own Sun. Understanding Alpha Centauri helps us understand our own cosmic history. Speaking of understanding our cosmic neighborhood, let's return for a moment to Proxima Centauri and its confirmed planets. While the scientists searching for planets around Alpha Centauri A and B have been using the challenging technique of direct imaging, the planets around Proxima were found using the radial velocity method. This technique measures the tiny back and forth motion of a star caused by the gravitational tug of orbiting planets. It's like watching someone being pulled around by an invisible dancing partner. You can't see the partner directly, but you can tell they're there from the way the visible person moves. Proxima Centauri B, discovered in 2016, was the first known planet orbiting our nearest stellar neighbor. It has a minimum mass of about 1.3 times the mass of Earth, making it solidly in the Earth-like category. It orbits Proxima Centauri once every 11.2 Earth days, which seems incredibly fast until you remember how dim and small Proxima Centauri is. Because the star is so faint, a planet has to orbit very close to receive enough warmth for liquid water. Proxima B sits only about 7.5 million kilometers from its star, roughly 20 times closer than Earth is to the Sun. At that distance, Proxima B is almost certainly tidally locked to its star. This means one side of the planet always faces the star, bathed in eternal daylight, while the other side faces away into eternal night. The boundary between these two hemispheres would be a permanent twilight zone, a ring of perpetual dusk and dawn circling the entire planet. On the day side, temperatures might be scorching, while on the night side, they might plunge far below freezing. But in that twilight band between, conditions might be just right. The habitability of tidally locked planets is a topic of intense scientific debate. Some researchers argue that the extreme temperature differences between the day and night sides would create violent weather patterns, with constant hurricane-force winds howling from the day side to the night side. Others suggest that if the planet has an atmosphere thick enough to redistribute heat, temperatures across the surface might be surprisingly moderate. Still others worry that the star's frequent flares would strip away any atmosphere long before such equilibrium could be established. In 2019, astronomers using the ALMA radio telescope detected what appeared to be a massive stellar flare from Proxima Centauri. At its peak, this flare was 10 times brighter than the largest flares ever observed on our Sun when measured at similar wavelengths. If Proxima B happened to be on the wrong side of the star during that event, it would have been blasted with enough radiation to potentially sterilize its surface and strip away significant portions of any atmosphere it possessed. And here's the troubling part. Such flares are not rare events for Proxima Centauri. They happen regularly, multiple times per year, sometimes multiple times per month. Over the 4.5 billion years that Proxima B has likely existed, the planet would have endured countless such bombardments. Any early atmosphere it formed might have been eroded away long ago. Any early oceans might have been boiled off into space. Any early life, if it ever arose, might have been repeatedly wiped out. But life is remarkably resilient. On Earth, we have found organisms thriving in the most extreme environments imaginable. Bacteria living in boiling hot springs. Microbes surviving in Antarctic ice. Creatures dwelling in the crushing darkness of deep-sea hydrothermal vents, completely isolated from sunlight. If life ever got started on Proxima B, it might have found refuges underground, protected from the stellar radiation by layers of rock and soil. Or it might have adapted to the harsh conditions in ways we cannot even imagine. Recent research has offered some hope. Studies using sophisticated computer models have shown that certain types of atmospheres could provide enough protection from Proxima Centauri's flares to allow life to survive. An atmosphere rich in carbon dioxide, for instance, might absorb much of the harmful radiation before it reaches the surface. And some experiments have shown that certain microorganisms can survive exposure to the kind of radiation that Proxima B might experience, at least for short periods. The question of whether Proxima B is habitable remains open. We will not know the answer until we can actually study the planet in detail. And that brings us back to the James Webb Space Telescope and why its observations of the Alpha Centauri system are so important. Webb is teaching us how to study nearby star systems, developing techniques that will eventually be applied to Proxima Centauri as well. Every observation brings us closer to understanding whether our nearest cosmic neighbors might harbor worlds where life could exist. Now, I want to take you deeper into the science behind these discoveries. Let's talk about how the James Webb Space Telescope actually works, because understanding the instrument helps you appreciate just how remarkable these observations truly are. Webb is not like a typical telescope you might imagine, with a single glass lens or mirror. It is a marvel of engineering unlike anything humans have ever built before. At the heart of Webb is its primary mirror, a honeycomb of 18 hexagonal segments coated in gold. These segments work together to form a single mirror 6.5 meters across, more than 2.5 times the diameter of the Hubble Space Telescope's mirror. But Webb couldn't be launched as a single large mirror because no rocket is big enough to carry something that size. Instead, the mirror segments were designed to unfold like origami after launch, each one positioning itself with nanometer precision to create a perfect light-collecting surface. The gold coating on the mirrors serves a specific purpose. Gold is an excellent reflector of infrared light, the kind of light that Webb was primarily designed to detect. Everything in the universe that has any warmth to it emits infrared radiation. The warmer an object is, the shorter the wavelength of infrared it emits. By studying the infrared light from distant objects, Webb can learn about their temperature, their composition, and their physical conditions in ways that visible light telescopes cannot. But there's a problem with studying infrared light from space. Heat is everywhere. The telescope itself would emit infrared radiation if it were warm, washing out the faint signals from distant stars and planets. Even a warm human body emits more infrared radiation than many of the objects Webb is trying to study. To overcome this challenge, Webb had to be made extremely cold. The telescope orbits the Sun at a special point in space called L2, about 1.5 million kilometers from Earth. There, protected by a tennis court-sized sun shield made of 5 layers of specialized material. The telescope's mirrors and instruments are cooled to temperatures below -200 degrees Celsius. That is colder than any natural environment on Earth, colder even than the surface of Pluto. At these temperatures, Webb's own infrared emissions are suppressed enough that it can detect the faint warmth of distant planets and the glow of the earliest galaxies in the universe. The Mid-Infrared Instrument, or MIRI, the tool used to search for planets around Alpha Centauri, is the coldest instrument on Webb. It operates at temperatures below 7 Kelvin, just 7 degrees above absolute zero. At these frigid temperatures, MIRI can detect light with wavelengths between 5 and 28 micrometers, far beyond what our eyes can see. This is the wavelength range where planets shine most brightly compared to their parent stars, making MIRI an ideal tool for planet hunting. But even with all this technology, directly imaging a planet around Alpha Centauri A was tremendously difficult. The star is so bright that even with the coronagraph blocking most of its light, residual glare still overwhelms faint nearby objects. The team had to develop special techniques to subtract this remaining light, using reference images of other stars and sophisticated computer algorithms to tease out any faint signals hiding in the glare. And they had to deal with the fact that Alpha Centauri is a binary system. When you block the light from Alpha Centauri A, you still have to contend with scattered light from Alpha Centauri B, which is nearby in the sky. The telescope's optics create complex patterns of light that interweave and overlap, making it incredibly challenging to identify a real planetary signal amid all the optical artifacts. It is like trying to spot a single grain of sand on a beach, while someone shines a flashlight in your eyes and throws handfuls of glitter in the air. The fact that the team found anything at all is a testament to the extraordinary capabilities of the James Webb Space Telescope and the skill of the scientists operating it. These observations are pushing the telescope to its absolute limits, attempting feats that would have been impossible with any previous instrument. And even if the candidate planet around Alpha Centauri A turns out to be a false alarm, the techniques developed during this search will be invaluable for future observations of other nearby star systems. This brings us to a profound question. Why does it matter? Why should we care whether there are planets around Alpha Centauri? After all, even at 4 light years, these worlds are far beyond our reach. No spacecraft we have ever built could get there in a human lifetime. No signal we send would arrive for years, and any response would take years more to return. What difference does it make if there are planets there or not? The answer has to do with something fundamental about human nature. We are explorers. We are curious beings who cannot help but wonder what lies beyond the next hill, beyond the next ocean, beyond the next star. For most of human history, the stars were unreachable points of light, beautiful but forever distant. The planets orbiting them were pure speculation, the stuff of science fiction and philosophical musing. But now, for the first time in history, we can actually see these other worlds. We can study them, measure them, learn about them. The discovery of exoplanets has transformed our understanding of our place in the universe. We now know that planets are common, that rocky worlds in habitable zones are not rare, that the universe is teeming with potential homes for life. And Alpha Centauri, as our nearest neighbor, holds a special place in this cosmic census. If there are planets around Alpha Centauri, they will be the first worlds we explore beyond our solar system. Not with humans, at least not initially, but perhaps with robotic probes, perhaps with telescopes so powerful they can analyze the atmospheres of these worlds and search for signs of biology, perhaps someday with signals sent across the void, searching for anyone who might be listening. There is a project called Breakthrough Starshot that aims to do exactly this. Funded by private investment, Starshot proposes to send tiny spacecraft, each weighing only a few grams, on a journey to the Alpha Centauri system. These spacecraft would be equipped with light sails, thin reflective surfaces that catch the pressure of laser light like a sail catches wind. By focusing an enormous array of ground-based lasers on these light sails, the team believes they could accelerate the tiny probes to 20% of the speed of light. At that speed, the journey to Alpha Centauri would take about 20 years. That is still a long time by human standards, but it is within a single human lifetime. A probe, launched when a child is born, could arrive at Alpha Centauri before that child finishes college. The data it sends back would take another 4 years to reach Earth, but within 25 years of launch, we could have close-up images of another star system. We could know for certain whether planets exist there. We could perhaps even detect signs of life. The challenges facing Breakthrough Starshot are immense. Building a spacecraft that weighs only a few grams, but can survive a journey through interstellar space, is extraordinarily difficult. The tiny probe would have to endure collisions with atoms of interstellar gas, impacts from dust particles, and the extreme conditions of space for 2 decades without any possibility of repair. The laser array needed to accelerate the probes would have to be powerful beyond anything currently in existence, requiring international cooperation and enormous investment. And yet, the project continues. Engineers are working on the tiny spacecraft, testing prototypes and refining designs. Physicists are studying the laser arrays, calculating power requirements and developing new technologies. The dream of reaching the stars is no longer just a dream. It is becoming an engineering problem, a challenge that human ingenuity is slowly, steadily beginning to address. The recent discoveries around Alpha Centauri only add fuel to this fire. If the candidate planet around Alpha Centauri A is confirmed, it would provide a tangible target for any interstellar mission. Not just a star, but a world. A place where our robotic emissaries could actually arrive and gather data. A destination that feels real and concrete, not abstract and theoretical. The psychology of exploration matters. Having a specific goal, a specific place to reach, motivates effort in ways that vague aspirations never can. But even without interstellar travel, studying Alpha Centauri teaches us about ourselves. The Alpha Centauri system is a natural laboratory for studying how planets form around sun-like stars. By understanding what kinds of planets exist there and how they came to be, we gain insights into the history of our own solar system. Why did Earth end up where it is? Why do we have one large moon instead of many small ones? Why is there a giant planet called Jupiter in the outer solar system? These questions about our cosmic home can be illuminated by studying our cosmic neighbors. And there is something else, something harder to quantify, but no less important. Looking toward the stars connects us to something larger than ourselves. In our daily lives, we are caught up in the immediate concerns of work and family, bills and obligations, news cycles and social media feeds. But when we look up at the night sky, we are reminded that we are part of a vast and ancient universe, that we are made of atoms forged in the hearts of stars, that our planet is one world among countless worlds, orbiting one star among hundreds of billions of stars, in one galaxy among trillions of galaxies. This perspective is humbling. It can make our daily worries seem small and insignificant, but it can also be inspiring. We are, as far as we know, the only beings in the universe who look up at the stars and wonder. The only creatures who build telescopes and space probes and try to understand the cosmos. The only species that dreams of crossing the void to visit other worlds. That makes us special, even as it makes us small. The James Webb Space Telescope, floating silently in the darkness beyond the Moon, is an expression of this human drive to explore and understand. It represents the culmination of decades of engineering, the collaboration of thousands of scientists and engineers across multiple countries, and an investment of billions of dollars. And what it gives us in return is knowledge, the most valuable thing of all. Knowledge of distant galaxies and nearby planets. Knowledge of how stars are born and how they die. Knowledge of our place in the cosmic order. Now let's return to our story and dive deeper into what the future might hold for the study of Alpha Centauri. The observations in 2024 were just the beginning. If the candidate planet is real, astronomers will want to observe it again and again, tracking its orbit, measuring its brightness at different wavelengths, and learning everything they can about its properties. But even if this particular candidate turns out to be a false alarm, the search will continue. New telescopes are being planned and built that will have even greater capabilities than Webb. The Nancy Grace Roman Space Telescope, scheduled to launch by 2027, will carry instruments specifically designed for direct imaging of exoplanets. Its coronagraph will be able to block starlight with unprecedented precision, potentially revealing planets that are currently hidden in the glare. If planets exist around Alpha Centauri A or B, Roman may be able to find them and study them in detail. Ground-based telescopes are also pushing the boundaries of what is possible. The extremely large telescope, being constructed in Chile, will have a primary mirror nearly 40 meters across. Combined with adaptive optics that correct for the blurring effects of Earth's atmosphere, this massive telescope will be able to image planets around nearby stars with remarkable clarity. It may even be able to detect signs of atmospheres on small rocky planets, opening up entirely new avenues of research. And then there are the proposed missions that exist only on paper, ambitious concepts that may or may not ever be built. Some astronomers dream of a space telescope with a starshade, a separate spacecraft that would fly tens of thousands of kilometers ahead of the telescope and unfold into a huge flower-shaped structure. This starshade would block the light of a target star, creating an artificial eclipse that would allow the telescope behind it to see any planets orbiting the star without the complications of a coronagraph. Such a mission could potentially image Earth like planets around Alpha Centauri and measure their spectra, searching for signs of oxygen, water vapor, and other molecules that might indicate the presence of life. The technology for such missions is still in development. The challenges are formidable. Flying two spacecraft in formation tens of thousands of kilometers apart, maintaining alignment to within a fraction of a millimeter, is extraordinarily difficult. The starshade itself would need to be tens of meters across, yet light enough to be launched into space and maneuvered into position. But engineers are working on solutions, testing prototypes, and gradually turning science fiction into engineering reality. In the meantime, we continue to learn from every observation Webb makes. Each image of the Alpha Centauri system, whether it reveals a planet or not, teaches us something new about the limits of our instruments and techniques. Each analysis of the data refines our understanding of how to extract faint signals from overwhelming noise. Science progresses one step at a time, building on previous work, learning from mistakes, and gradually expanding the boundaries of what we know. Let's pause for a moment and consider what we have learned about the Alpha Centauri system. We know it consists of 3 stars bound together by gravity. Alpha Centauri A is a yellow sun-like star, slightly larger and brighter than our own sun. Alpha Centauri B is a smaller orange star that orbits together with A in a dance lasting nearly 80 years. And Proxima Centauri is a tiny red dwarf star orbiting the main pair at a vast distance, taking more than 500,000 years to complete one circuit. Around Proxima Centauri, we have confirmed the existence of at least 2 planets. Proxima B is an Earth-sized world in the habitable zone, though its prospects for habitability are complicated by the frequent flares of its parent star. Proxima D is a smaller world orbiting closer to the star, likely too hot for liquid water. Around Alpha Centauri A, we now have tantalizing hints of a possible Saturn mass planet. If confirmed, this would be the closest planet ever directly imaged around a sun-like star. It would orbit in a path that carries it through the habitable zone, possibly influencing the formation and survival of any smaller rocky worlds in the system. Around Alpha Centauri B, we have not yet found any confirmed planets. Some previous claims of planet detections have turned out to be artifacts of data processing or stellar activity masquerading as planetary signals. But absence of evidence is not evidence of absence. Planets may well exist around Alpha Centauri B, waiting to be discovered by future observations with improved instruments and techniques. Taken together, this information paints a picture of a stellar neighborhood that is both similar to and different from our own solar system. Like our Sun, Alpha Centauri A and B are stable, long-lived stars capable of hosting planetary systems. Like our solar system, the Alpha Centauri system may contain both giant planets and smaller rocky worlds. But the gravitational dynamics of a triple star system are far more complex than those of a single star, creating environments where planet formation and orbital stability face different challenges. This complexity is part of what makes the Alpha Centauri system so scientifically valuable. By studying how planets form and survive in such a complicated environment, we gain insights that cannot be obtained from studying simpler single-star systems. We learn about the range of conditions under which planets can exist, the diversity of architectures that planetary systems can adopt, and the prevalence of worlds like Earth across the galaxy. Now I want to talk about something that might seem like science fiction, but is actually serious science. What would it take for life to exist on a planet orbiting Alpha Centauri A? If the candidate planet is confirmed and it does have moons, could any of those moons harbor conditions suitable for life? The question of extraterrestrial life is one of the oldest and most profound in all of human inquiry. For most of history, it was purely philosophical, a matter for speculation and argument, without any way to test the competing hypotheses. But in the past few decades, we have begun to accumulate actual data. We have discovered thousands of exoplanets, some of them in habitable zones where liquid water might exist. We have found organic molecules in interstellar space, the building blocks of life scattered throughout the cosmos. We have studied extreme environments on Earth and found life thriving in conditions once thought impossible. These discoveries have shifted the question from whether life could exist elsewhere to whether life does exist elsewhere. And if life has arisen on other worlds, the nearest place to look for evidence is right in our cosmic backyard. Proxima B is closer than any other known potentially habitable world. A future mission that could detect biosignatures in its atmosphere would answer one of the greatest questions in the history of science. But what would biosignatures look like? How would we recognize evidence of life on a distant planet? The most commonly discussed biosignature is oxygen. On Earth, oxygen makes up about 21% of our atmosphere. But this oxygen does not come from geological processes. It is produced by photosynthetic organisms, plants and cyanobacteria that use sunlight to convert carbon dioxide and water into sugars and oxygen. Without life, Earth's atmosphere would have almost no oxygen at all. So if we found a planet with significant oxygen in its atmosphere, that would be strong evidence for biological activity. Not conclusive, mind you. There are some non-biological processes that can produce oxygen, but combined with other indicators, like the presence of methane, which reacts quickly with oxygen and would need to be constantly replenished, the detection of oxygen would be highly suggestive. Other potential biosignatures include the spectral signatures of chlorophyll, the green pigment that plants use to capture sunlight. If a planet's surface were covered with vegetation, we might be able to detect the distinctive way chlorophyll reflects and absorbs light. We might also look for industrial pollutants, chemicals that are only produced by technological civilizations. Detecting such pollutants would indicate not just life, but intelligent, industrialized life. Of course, we have to be careful not to let our expectations blind us to possibilities we haven't considered. Life on other worlds might not use the same biochemistry as life on Earth. Alien plants might not use chlorophyll. Alien metabolisms might produce different waste gases. We need to keep our minds open to the unexpected, while still looking for the signatures we know how to recognize. The search for life around Alpha Centauri is just beginning. The current observations are focused on detecting and characterizing planets. Once we know what kinds of worlds exist there, we can start thinking about how to study their atmospheres and surfaces in more detail. Each step builds on the previous one, gradually filling in our picture of our nearest stellar neighbors. Let me take you on a mental journey now. Imagine, if you will, that you are standing on the surface of a moon orbiting the candidate planet around Alpha Centauri A. Your spacesuit protects you from the vacuum, and you look up at a sky unlike any seen from Earth. Dominating your view is the giant planet itself, a massive ball of swirling clouds banded with browns and tans and subtle blues. It hangs in the sky far larger than our moon appears from Earth, its vast bulk a constant presence, whether it is day or night. Beyond the planet, two suns shine in the sky. Alpha Centauri A, the primary, blazes with a warm yellow light much like our sun, but perhaps seeming slightly larger and brighter. And in the distance, Alpha Centauri B glows with an orange hue, bright enough to cast shadows but clearly the junior partner in this cosmic dance. The two stars move across the sky in complex patterns, sometimes appearing close together, sometimes opposite each other, depending on where they are in their 80-year orbit. The lighting on your moon would be unlike anything experienced on Earth. For part of each month, you might have two sets of shadows as both stars shine from different directions. At other times, you might have extended twilight periods as one star sets while the other remains in the sky. The colors of sunrise and sunset would shift depending on which star was involved. Sometimes golden, sometimes orange, sometimes a mixture of both. If you could look toward the sky in the direction of Earth's sun, you might see a faint star among many others. From Alpha Centauri, our Sun would appear as just another point of light in the constellation Cassiopeia, the distinctive W shape distorted by the addition of a new bright star. Our entire solar system, all our history and struggles and achievements, would be invisible from that distance. Just a single unassuming star among billions. This perspective shift is one of the most profound gifts of astronomy. It reminds us that our world, as precious and unique as it is to us, is one small place in an enormously vast universe. The problems that consume our attention, the conflicts that divide our societies, the dramas of our daily lives, all occur on a single pale blue dot orbiting an ordinary yellow star in an unremarkable corner of an average spiral galaxy. And yet, from that pale blue dot, we have reached out with our minds and instruments to touch the stars. Let's talk now about what happens next in the search for planets around Alpha Centauri. The James Webb Space Telescope has a busy schedule, with astronomers from around the world competing for precious observation time. But the Alpha Centauri team has been granted additional opportunities to observe the system. They will watch and wait for the candidate planet to reappear, hoping to catch it at a different point in its orbit. If they can detect it multiple times at different positions, that would provide strong confirmation that the signal is real. Meanwhile, other teams are pursuing different approaches. Some are using ground-based telescopes with adaptive optics to search for planets in the Alpha Centauri system. Others are analyzing archival data from previous observations, looking for hints that might have been missed. The hunt for planets around Alpha Centauri has become one of the most active areas of exoplanet research, drawing attention from astronomers across multiple continents. The stakes are high. A confirmed planet around Alpha Centauri A would be a landmark discovery, the first world directly imaged in the habitable zone of a sun-like star. It would demonstrate that the techniques being developed for direct imaging actually work, opening the door to similar observations of other nearby star systems. And it would provide a concrete target for future missions, both robotic and perhaps someday crewed. But even if the candidate planet turns out to be an artifact, the search has value. Science learns as much from null results as from positive ones. If the signal is not a planet, understanding what it actually is will improve our techniques for future observations. Every blind alley explored is one fewer blind alley that remains to be ruled out. Progress in science is not always a straight line forward. Sometimes it zigzags, backtracks, and spirals. But it always moves, always advances, always brings us closer to understanding. Now I want to address a question that might be forming in your mind. With all this talk of distant stars and possible planets, what does any of this have to do with your daily life? Why should you, drifting off to sleep as you listen to this video, care about what the James Webb Space Telescope found around Alpha Centauri? The answer is both practical and profound. On the practical side, the technologies developed for space exploration have transformed life on Earth in countless ways. The sensors in your smartphone, the materials in your clothing, the medical imaging devices at your doctor's office, all trace their ancestry to space programs and astronomical research. The pursuit of knowledge about the cosmos drives innovation that benefits everyone. But more than that, astronomy feeds something essential in the human spirit. We are storytelling creatures. We need narratives that make sense of our lives and our place in the world. For most of human history, those narratives were limited to our own planet, our own species, our own small corner of existence. But now we know we are part of a much larger story. The story of a universe that began nearly 14 billion years ago with a cataclysmic expansion we call the Big Bang. A universe where matter condensed into stars, stars forged heavy elements in their cores, and those elements became the raw materials for planets, for life, for us. Understanding this story is not just an intellectual exercise. It changes how we see ourselves and each other. When you look at another human being, you are looking at a collection of atoms that were forged in the hearts of ancient stars, assembled over billions of years into the complex structures that make up a person. Every breath you take contains oxygen that was released by photosynthetic organisms billions of years ago. Every beat of your heart pumps blood rich with iron that was created in supernova explosions before our solar system even existed. We are quite literally children of the cosmos, made of star stuff, to use Carl Sagan's famous phrase. And the discoveries being made about Alpha Centauri and other star systems remind us of this kinship. Those distant worlds are made of the same elements as our own. The same physical laws govern the formation of planets there as here. The same chemistry that led to life on Earth might have led to life elsewhere. We are not isolated. We are part of a vast and intricate tapestry that spans billions of years and billions of light years. This perspective can be comforting as you drift off to sleep. Whatever worries are on your mind, whatever challenges you face, you are participating in something much larger than yourself. The universe is vast and ancient and mostly indifferent to human concerns. But within that vastness, on this one small planet, consciousness has emerged. Awareness has emerged. The ability to wonder and question and explore has emerged. And you are part of that. Now let us continue our journey through the Alpha Centauri system, exploring what we know and what we hope to learn. I want to tell you more about the remarkable star at the center of recent discoveries, Alpha Centauri A, and why astronomers are so fascinated by it. Alpha Centauri A is what astronomers call a G-type main sequence star. This classification places it in the same category as our Sun. Both stars generate energy by fusing hydrogen atoms into helium in their cores, a process that has been going on for billions of years and will continue for billions more. Both have similar surface temperatures, around 5,800 degrees, giving them that characteristic yellow-white color. But there are subtle differences. Alpha Centauri A is about 10% more massive than our Sun, which means it has slightly more fuel to burn. You might think this would give it a longer lifetime, like having a bigger gas tank in your car. But in stellar physics, the opposite is true. More massive stars burn their fuel faster, not slower. They live bright and die young, relatively speaking. Our Sun, at about 4.5 billion years old, is roughly middle-aged for a G-type star. It will continue fusing hydrogen for another 5 billion years or so before beginning its transformation into a red giant. Alpha Centauri A, being slightly more massive and about the same age, is perhaps a bit further along in its evolution. But both stars have billions of years of stable burning ahead of them, plenty of time for any planets in their systems to develop complex environments, perhaps even life. The similar age and composition of Alpha Centauri A and our Sun raises interesting questions about planetary formation. Our Sun formed from a cloud of gas and dust about 4.6 billion years ago. The planets of our solar system formed from the leftover material that did not fall into the Sun, condensing into rocky worlds close in and gas giants further out. We have spent decades studying our own solar system, learning how the planets formed and evolved. But we have only one example to study. A sample size of one makes it hard to know what is typical and what is unusual. Is our solar system's architecture, with rocky planets close in, gas giants further out, and a population of icy bodies beyond common? Or is it rare, a fluke of our particular formation history? By studying other star systems, especially ones around stars similar to our Sun, we can begin to answer these questions. The candidate planet around Alpha Centauri A, if confirmed, would be a gas giant at about 2 astronomical units from its star. In our solar system, that would place it roughly where the asteroid belt is between Mars and Jupiter. This is interesting because it differs from our solar system's architecture. We have no gas giant in our asteroid belt. Our nearest gas giant, Jupiter, is about 5 astronomical units from the Sun. Does this mean gas giants can form closer to Sun-like stars than they did in our system? Or was this planet formed elsewhere and migrated inward over time? These questions touch on one of the most active areas of exoplanet research. We have found many hot Jupiters, giant planets orbiting extremely close to their stars, much closer than Mercury is to our Sun. These worlds cannot have formed where we find them. The temperatures so close to a star would have prevented giant planet formation. They must have migrated inward after forming further out. Perhaps the candidate planet around Alpha Centauri A underwent a similar migration, though not as extreme. Perhaps it formed at a greater distance and gradually spiraled inward as it interacted with the disk of gas and dust that surrounded the young star. Or perhaps the gravitational influence of Alpha Centauri B, orbiting nearby, stirred up the young planetary system and sent planets careening onto unusual orbits. The dynamics of planet formation in binary systems are fiercely complex. 2 stars orbiting each other create a gravitational environment that is constantly shifting. Regions that are stable at one point in the orbit may become unstable at another. Material that would calmly orbit a single star might be pulled and stretched by the competing gravity of 2 stars. Planets can be ejected from the system entirely if they wander too close to one star, while the other is passing by. And yet, despite all these challenges, planets do form in binary systems. We have found them. Not as commonly as around single stars, perhaps, but they exist. The Alpha Centauri system, with its 2 Sun-like stars orbiting each other at relatively close distances, represents one of the more challenging environments for planet formation. If giant planets can form and survive there, it tells us that planetary systems are even more resilient and diverse than we might have expected. Now let's turn our attention to Alpha Centauri B, the orange companion star. Ptolemy, as it is formally named, has received less attention than its larger sibling in recent years, but it remains an intriguing target for planet hunters. At 90% the mass of our Sun, it is still a respectable star, capable of hosting its own planetary system. In 2012, a team of astronomers announced the discovery of a planet orbiting Alpha Centauri B. This world, designated Alpha Centauri BB, would have been slightly more massive than Earth and orbiting extremely close to the star, completing one orbit every 3¼ days. The discovery made headlines around the world. An Earth-mass planet around our nearest stellar neighbor. It seemed too good to be true, and unfortunately, it was. Subsequent analyses of the data raised doubts about the claimed detection. The signal that had been interpreted as a planet turned out to be an artifact of the complex data processing required to extract such tiny signals from noisy observations. Alpha Centauri B is an active star, with spots and flares that mimic the subtle signals planets produce. Distinguishing a real planet from stellar activity is extraordinarily difficult, and in this case, the initial analysis had been too optimistic. The retraction of the Alpha Centauri BB discovery was a disappointment, but it was also a valuable lesson. It reminded astronomers how challenging the search for planets around nearby stars can be. It spurred improvements in data analysis techniques and increased caution about announcing discoveries before they could be thoroughly vetted. Science is self-correcting. When mistakes are made, they are eventually found and fixed. The process can be messy and embarrassing, but it leads us closer to the truth. Today, no planets have been confirmed around Alpha Centauri B, but that does not mean none exist. The techniques that failed to detect planets a decade ago have improved enormously. New instruments, new algorithms, and new observational strategies are being developed. The search continues. Somewhere around that orange star, planets may be waiting to be found, their presence hidden in the noise, but gradually becoming detectable as our tools grow sharper. Let us take a moment to appreciate the scale of what we have accomplished. A century ago, we did not even know for certain that galaxies existed beyond our own Milky Way. The famous debate between Harlow Shapley and Heber Curtis in 1920 argued over whether the spiral nebulae seen in telescopes were clouds of gas within our galaxy or separate island universes far beyond it. Edwin Hubble settled the question in 1924 by measuring the distance to the Andromeda Nebula and showing it was far outside the Milky Way. 50 years ago, we had never detected a planet around another star. The existence of exoplanets was theorized but unproven. Some astronomers argued that planets should be common, others that they should be rare. Without data, the question could not be settled. The first confirmed exoplanets were discovered in 1992, orbiting a pulsar, the rapidly spinning remnant of an exploded star. The first exoplanet around a normal Sun-like star was found in 1995. Since then, we have found thousands. 20 years ago, the James Webb Space Telescope was still a concept on paper, years away from launch. The technologies it required had not yet been invented. The mirrors had not been ground. The instruments had not been built. The sunshield had not been woven. The idea of directly imaging planets around nearby stars was a distant dream. And now here we are. Webb is operational, floating serenely in space, transforming our understanding of the cosmos with every observation. We have potential evidence of a planet around our nearest sun, like stellar neighbor. We are developing plans for interstellar probes that might actually reach that neighbor within a human lifetime. The pace of discovery is breathtaking. What will we know 50 years from now? 100 years from now? It is impossible to say for certain. But if the past is any guide, we will know things we cannot currently imagine. We will have answered questions we have not yet thought to ask. We will have discovered wonders that would seem like magic to us today, just as our current discoveries would seem like magic to the astronomers of a century ago. This is the trajectory we are on, a trajectory of increasing knowledge, increasing capability, increasing understanding. It is not a straight line. There are setbacks and false starts and disappointments, but the overall trend is unmistakable. We are learning, we are growing, we are reaching out into the cosmos with ever greater skill and ambition. Now, I want to share with you some of the quiet poetry of astronomy. The science we have discussed is rigorous and technical, full of numbers and measurements and careful analysis. But behind all that precision lies something deeply human. a sense of wonder at the vastness and beauty of the universe, a longing to understand our place in the cosmic order, a quiet awe at the thought that we, beings evolved on one small planet, have somehow developed the ability to peer across trillions of miles and learn the secrets of other worlds. Think about what it means that light from Alpha Centauri, after traveling for more than 4 years across the void, enters the golden mirrors of the James Webb Space Telescope and is transformed into data that scientists can analyze. That light left its source before you could have known this video existed, before the specific events of your day-to-day had unfolded. Yet here you are, learning about what that ancient light revealed, connected across space and time to a star system that has been our neighbor since the formation of the solar system. The stars of Alpha Centauri have witnessed the entire history of life on Earth. They were already shining when the first single-celled organisms appeared in our oceans. They burned on as life slowly evolved, eventually crawling onto land, developing intelligence, building civilizations. They are still shining now as we send telescopes into space to study them, and they will continue to shine for billions of years after we are gone. This temporal perspective can be both humbling and comforting. Humbling because it reminds us of our insignificance in the cosmic timescale. We are here for such a brief moment, a flicker of consciousness in an ocean of time. But comforting too, because it connects us to something permanent. The stars were here before us and will be here after us. They are the constants against which our brief lives unfold. And for this moment, for this brief flicker, we have the privilege of looking up and trying to understand. Let me tell you about the night sky from Alpha Centauri's perspective. If you could transport yourself to a planet orbiting one of those stars and look back toward our Sun, what would you see? From that distance, our Sun would be a moderately bright star, visible to the unaided eye, but not particularly remarkable. It would appear in what we know as the constellation Cassiopeia, the distinctive W shape that Northern Hemisphere observers can see year-round. But from Alpha Centauri, our Sun would not be inside the W. It would be an additional star, sitting off to one side, changing the familiar pattern into something new. The locals, if there were any locals, would have different names for the constellations, different mythology, different ways of seeing meaning in the patterns of stars. Our Sun might be a guide star for their navigation, or the subject of their poetry, or just an unremarkable point of light among many. None of our planets would be visible from Alpha Centauri, even with good telescopes. Earth is far too small and faint to be detected at that distance with anything like current technology. The greatest achievements of human civilization, all our art and music and science, all our love and loss and longing, would be completely invisible from just 4 light years away. We would be nothing more than a few unresolved photons lost in the glare of an ordinary star. This perspective is important because it keeps us humble. When we search for planets around Alpha Centauri, we should remember that any beings living there would face exactly the same challenges searching for Earth around our Sun. The difficulty of exoplanet detection goes both ways. If we cannot easily find Earth-sized planets around Alpha Centauri, hypothetical Alpha Centaurians would have equal trouble finding Earth. The cosmos keeps its secrets well, revealing them only to those who build better telescopes and develop cleverer techniques. And yet, we persist. We build better telescopes. We develop cleverer techniques. We push against the limits of what is possible because we cannot help ourselves. Curiosity is coded into our DNA. The desire to know, to explore, to understand is as fundamental to human nature as the desire to eat or sleep or love. When we look at the stars and wonder what is out there, we are expressing something essential about who we are as a species. The search for planets around Alpha Centauri is part of a much larger human project, the project of understanding our universe and our place within it. Every observation with the James Webb Space Telescope, every hour of data analysis, every paper published in scientific journals is a small step forward in this grand endeavor. And every person who looks up at the night sky and wonders is participating in it, contributing to the collective consciousness that makes us human. As you listen to these words, perhaps growing sleepy as the hour grows late, I want you to know that the universe is a remarkable place. It is vast beyond comprehension, old beyond imagining, filled with wonders we have only begun to discover. And you are part of it. You are made of the same elements as the stars. Your atoms were forged in cosmic furnaces billions of years ago. You are, quite literally, the universe trying to understand itself. The planets of Alpha Centauri, if they exist, are our neighbors in this cosmic adventure. They orbit stars that we can see with our naked eyes, beaming their light across the void as they have for billions of years. Whether those worlds harbor life or stand as sterile monuments to the indifference of nature, they are connected to us by the fundamental laws of physics, the shared chemistry of the cosmos, and the curiosity that drives us to reach out across the light years. Now let us delve deeper into one of the most profound aspects of our story, the connection between Alpha Centauri and the future of humanity. As our civilization matures and our technology advances, we will eventually have to look beyond Earth for our long-term survival. Our planet, as beautiful and irreplaceable as it is, cannot sustain us forever. Resources are finite. The sun itself will eventually exhaust its fuel. On timescales of billions of years, we will need to find new homes among the stars. Alpha Centauri is the obvious first destination. It is the closest star system to our own, the first stepping stone on the path to becoming an interstellar species. Any practical interstellar travel technology we develop will almost certainly be tested first on a mission to Alpha Centauri. The light sails of Breakthrough Starshot, if they work, will fly to Alpha Centauri. The first humans to leave our solar system, if such a day ever comes, will likely set their course for Alpha Centauri. This is why the search for planets around Alpha Centauri matters so much. We are not just cataloguing distant worlds for academic interest. We are mapping the territory we hope our descendants will someday explore. Every discovery about the Alpha Centauri system is a piece of information that could be crucial for future generations. What kinds of planets are there? What are their orbits? What are their atmospheres made of? Where might future colonists find resources? Where might they face dangers? The candidate gas giant around Alpha Centauri A, if confirmed, would be one of the first landmarks on this map. A giant planet means gravitational influence that shapes the entire system. It means potential moons that might harbor their own environments. It means a source of hydrogen and helium that could be useful for future spacecraft. Even worlds that cannot support life directly can be valuable way stations on longer journeys. Of course, interstellar colonization is far in the future. The technologies required do not yet exist and may not exist for centuries. But science and engineering progress. Problems that seem insurmountable today may have elegant solutions tomorrow. A century ago, powered flight was barely a decade old. 2 decades later, we were flying across oceans. 2 decades after that, we were building jet aircraft. 2 decades beyond that, we walked on the moon. The pace of technological change is not linear. It accelerates. Perhaps in a century, the idea of sending robotic probes to Alpha Centauri will seem as routine as launching satellites does today. Perhaps in 2 centuries, the first crewed missions will be under consideration. Perhaps in a millennium, Alpha Centauri will be home to millions of human beings, their ancestors' bold journey a celebrated chapter in the history books. Or perhaps the challenges of interstellar travel will prove insurmountable, and we will remain forever bound to our solar system. We cannot know for certain, but we can prepare, and part of preparing is learning everything we can about our nearest stellar neighbors. Let us return to the James Webb Space Telescope and consider what other secrets it might reveal about the Alpha Centauri system. The observations in 2024 focused on direct imaging, trying to photograph planets by blocking out starlight. But Webb has other tools in its arsenal. Its spectrographs can spread light into its component wavelengths, revealing the chemical composition of whatever it observes. If a planet transits across the face of its star, Webb can study the starlight that passes through the planet's atmosphere, identifying gases present in that atmosphere. Unfortunately, the candidate planet around Alpha Centauri A is not in an orbit that causes it to transit from our perspective. The geometry is wrong. We see the system from a different angle. But this does not mean atmospheric studies are impossible. Future instruments, more sensitive and precise than Webb's, might be able to detect the faint glow of the planet's atmosphere directly. They might measure the planet's temperature, determine its composition, and learn about its cloud structures. The search for smaller, rockier planets in the system continues as well. While the gas giant candidate has grabbed headlines, astronomers are quietly analyzing data for any hint of smaller worlds. A rocky planet in the habitable zone of Alpha Centauri. A would be perhaps the most exciting discovery possible. It would be a world where liquid water might exist, where conditions might be suitable for life as we know it, sitting just over 4 light-years from Earth. Finding such a planet would be extraordinarily difficult. Rocky planets are much smaller than gas giants, reflecting and emitting far less light. They would be lost in the glare of their parent star, hidden among the noise and artifacts that plague all astronomical observations. But difficult does not mean impossible. With each passing year, our instruments grow more sensitive, our techniques grow more sophisticated, and our chances of detection improve. Meanwhile, the study of Proxima Centauri continues. Despite the challenges posed by its frequent flares, Proxima remains an important target. Its confirmed planet Proxima B is still the closest known potentially habitable world. If life could somehow survive the radiation environment around a flare star, Proxima B is where we might find evidence of it. Astronomers are working on ways to observe the planet more closely, searching for any signal that might indicate an atmosphere or surface features. One intriguing possibility involves detecting radio emissions from Proxima B. If the planet has a strong magnetic field, the interaction between that field and the stellar wind from Proxima Centauri might produce detectable radio signals. In 2020, astronomers reported a candidate signal from the direction of Proxima Centauri that initially caused great excitement. Dubbed BLC-1, the signal had characteristics that seemed artificial, sparking speculation about possible alien technology. But upon further investigation, the signal was traced to terrestrial interference, radio emissions from equipment on Earth that had been mistakenly identified as coming from space. It was a false alarm, Another reminder of how difficult it is to distinguish genuine extraterrestrial signals from the noise we ourselves generate. The universe is not easy to read. It speaks in whispers, and we must filter out the shouting of our own technologies to hear it. The search for technosignatures, evidence of technological civilizations elsewhere in the cosmos, is intimately connected to the study of nearby star systems like Alpha Centauri. If intelligent life exists anywhere in our galaxy, the closest examples would be the easiest to detect. Radio telescopes scan the skies for artificial signals. Lasers probe nearby stars for signs of communication beams. So far, we have found nothing definitive. The universe remains silent, at least to our ears. But absence of evidence is not evidence of absence, as the saying goes. Perhaps intelligent life is rare. Perhaps it exists, but does not use technologies we can detect. Perhaps civilizations routinely destroy themselves before achieving interstellar capability. Or perhaps we simply have not looked in the right place at the right time, with the right instruments. The search continues, and Alpha Centauri remains one of the prime targets. Now let me paint another mental picture for you. Imagine you are floating in space, halfway between our Sun and Alpha Centauri. You are in the depths of interstellar space, farther from any star than most humans have ever contemplated. In every direction, the stars appear as pinpricks of light against the infinite black. There is no up or down, no left or right, only the vast emptiness punctuated by distant suns. From this vantage point, our Sun and Alpha Centauri are both visible as ordinary-looking stars, separated by a gap that seems small in angular terms, but represents trillions of kilometers of actual distance. The 2 light years you have traveled seem impossibly far, yet you are only halfway. Another 2 light years of nothing but vacuum and radiation and cold darkness await you. This is what interstellar space is really like. Empty beyond comprehension, cold beyond endurance, dark beyond imagination. The space between stars is not merely empty, it is defined by its emptiness. The few atoms of hydrogen and helium scattered through each cubic centimeter do nothing to fill the void. The occasional dust grain drifting through adds nothing to the desolation. This is the medium through which any interstellar travelers, whether robotic or biological, must pass. The challenges of crossing this void are immense. Spacecraft must carry or generate their own energy, as there is no sunlight to provide power. They must navigate with extreme precision, as even small errors over such distances lead to missing targets by millions of kilometers. They must survive for decades without maintenance, as no repair crews will be available in interstellar space. They must protect themselves from cosmic radiation, from impacts with dust particles that become lethal projectiles at high speed, from the simple wear of time on components and systems. And yet, as we have discussed, engineers are working on solutions. Light sails that can be pushed to tremendous speeds by laser beams, miniaturized electronics that can pack remarkable capability into gram-scale packages, materials that can withstand the rigors of space for decades or centuries. The problems are hard but not impossible. They yield, slowly but surely, to human ingenuity and persistence. Consider what the journey to Alpha Centauri might be like for a tiny probe traveling at 20% of the speed of light. Accelerating from Earth orbit, pushed by the concentrated light of a powerful laser array, the probe would reach its cruise velocity in a matter of minutes. From that point on, it would coast through space unpowered, steadily closing the gap to its target. At 20% of the speed of light, roughly 60,000 kilometers per second, the probe would cover about 1 light year every 5 years. After 5 years, it would pass the point where we currently are in our mental journey. After 10 years, it would be 3/4 of the way there. After 15 years, it would be approaching the outer reaches of the Alpha Centauri system. After 20 years, it would arrive. During that entire journey, the probe would be on its own. Light takes time to travel. A signal sent from Earth when the probe was 10 years into its journey would take 2 years to reach it. Any response would take 2 more years to return. By the time mission controllers on Earth received news that the probe was experiencing a problem, 4 years would have passed. No real-time intervention would be possible. This is why the probe would need to be autonomous, capable of making decisions on its own. If it encountered an unexpected obstacle, it would need to navigate around it without waiting for human guidance. If its instruments detected something interesting, it would need to decide how to respond. The probe would be, in a very real sense, an independent explorer, an ambassador of humanity venturing into territory no human had ever seen. When the probe finally reached Alpha Centauri, it would face a final challenge. Moving at 20% of the speed of light, it would not have the fuel to slow down. It would flash through the system in a matter of hours, taking pictures and collecting data as fast as its instruments could operate. Then it would continue on, leaving Alpha Centauri behind, sailing into the galaxy forever. This flyby approach is simpler than trying to enter orbit, which would require carrying enough fuel to decelerate an impossibly large mass. But it means the probe would have only one chance to gather data. Every image, every measurement, every bit of information would need to be captured during the brief window of close approach. The engineering challenges are formidable, but the potential rewards are extraordinary. Imagine receiving the first close-up images of a planet orbiting another star. After decades of fuzzy blobs and indirect measurements, suddenly seeing surface features, clouds, perhaps even oceans or continents. The emotional impact would be overwhelming. The scientific value would be incalculable. The psychological effect on humanity, seeing tangible evidence of another world in such detail, might transform our species' view of itself and its place in the cosmos. This is what we are working toward. Not just the detection of exoplanets, but their exploration. Not just knowing that other worlds exist, but seeing them, studying them, understanding them. The James Webb Space Telescope is a crucial step on this path. Every observation it makes brings us closer to the day when we can truly visit our cosmic neighbors, even if only through robotic proxies. Now let us spend some time contemplating the philosophical implications of what we have discussed. The potential discovery of planets around Alpha Centauri raises profound questions about the nature of existence and the meaning of human life. For most of human history, we believed we were the center of everything. The Earth was the fixed point around which the sun, moon, and stars revolved. The heavens were perfect and unchanging, completely separate from the corruptible realm below. Humans were the pinnacle of creation, the purpose for which the entire universe existed. One by one, these beliefs have been overturned. Copernicus showed that the Earth moves around the sun, not vice versa. Galileo's telescope revealed imperfections on the moon and moons orbiting Jupiter. Darwin demonstrated that humans evolved from other life forms through natural processes. Einstein revealed that space and time are not absolute, but relative, malleable, strange. Hubble showed that our galaxy is just one among billions, our sun just one among hundreds of billions of stars. Each of these discoveries was disorienting for those who lived through them. To have your entire worldview upended, to learn that you are not as special as you thought. To realize that the universe is vastly larger and stranger than anyone imagined. These experiences can be profoundly unsettling. And yet, from our modern vantage point, we can see that each discovery also brought liberation. Freedom from false beliefs, freedom to explore the truth, freedom to wonder at the genuine marvels of reality rather than the artificial comforts of illusion. The discovery of planets around Alpha Centauri, and the eventual discovery of life beyond Earth if it happens, will be another such transformation. It will force us to reconsider our place in the cosmic order yet again. We may not be the only intelligent beings in the universe. We may not even be the only life in our local neighborhood. Our planet, as precious as it is, may be one of many habitats for biology in a cosmos teeming with living worlds. Some people find this prospect threatening. If we are not alone, if we are not special, what meaning does human life have? But I would suggest that the opposite is true. If life is common in the universe, it means that the cosmos is far more wondrous than we imagined. It means that the emergence of consciousness, of awareness, of the ability to wonder about the stars, is not a freak accident, but a natural outcome of the laws of physics operating over cosmic time. It means that we are part of something much larger than ourselves, connected to a galactic or even universal community of life. And even if we are alone, even if Earth is the only island of life in an otherwise sterile universe, that too carries profound meaning. It means that we are precious beyond measure. It means that in all the billions of galaxies and trillions of stars, only here has matter organized itself into forms capable of love and art and music and science. It means that our responsibility to preserve and cherish life is absolute, because nowhere else in the cosmos does it exist. Either way, whether life is common or rare, the search for planets and the exploration of nearby star systems enriches our understanding of existence. It gives us context for our own world. It inspires us to reach beyond our limitations. It connects us to the grand sweep of cosmic history in which we are privileged to participate for this brief moment. As you drift towards sleep, let these thoughts settle into your mind. You are a temporary configuration of atoms that have been cycling through the cosmos for billions of years. The carbon in your body was forged in the core of a massive star and scattered into space when that star exploded. The oxygen you breathe was released by ancient organisms in primordial oceans. The iron in your blood came from the cataclysmic merger of neutron stars, some of the most violent events in the universe. You are stardust contemplating the stars, atoms arranged into patterns capable of looking back at the furnaces that created them. This is not poetry, though it is poetic. It is simple fact. And when we look at Alpha Centauri, we are looking at sibling stars, born from the same galactic material as our Sun, shining with the same nuclear fire, possibly hosting worlds made of the same fundamental elements as Earth. The universe made us, and now we are trying to understand the universe. There is something beautiful and recursive about this. The cosmos examining itself through our eyes and instruments, the vast becoming aware through the small, the ancient contemplated by the brief. Let me tell you more about the night sky, as seen from different perspectives in the Alpha Centauri system. We have imagined standing on a moon of the candidate planet around Alpha Centauri A. But what about standing on Proxima B, the Earth-sized world orbiting the tiny red dwarf? If you could stand on Proxima B and look up at the sky, your experience would be utterly alien compared to Earth. Your sun, Proxima Centauri, would appear much larger in the sky than our sun does from Earth. Because Proxima B orbits so close to its star, the red dwarf would span about 3 degrees of arc, roughly 6 times the width of our Sun as seen from Earth. But despite its apparent size, Proxima Centauri would provide only dim illumination, its feeble output painting the world in perpetual rusty twilight. The star would barely move across the sky if it moved at all. Proxima B is almost certainly tidally locked, one face always turned toward the star, one face always turned away. If you stood on the day side, Proxima Centauri would hang forever in the same spot overhead, never rising, never setting, just sitting there like a great red eye watching the landscape below. The shadows it cast would be permanent, stretching endlessly across the terrain. In the sky, beyond Proxima Centauri, you might see 2 other bright stars. These would be Alpha Centauri A and B, the larger companions to your dim little Sun. From Proxima's perspective, they would appear close together, bright enough to cast their own shadows during Proxima's night. Depending on where they were in their 80-year orbit around each other, they might appear as a single brilliant point, or as 2 distinct golden and orange lights. And somewhere in that sky, if you knew where to look, you might find a faint yellowish star that means nothing to the hypothetical inhabitants of Proxima B. That star would be our Sun, Saul, unremarkable from such a distance. Earth and all its history would be invisible, just part of the unresolved glow of an ordinary G-type star. The weather on Proxima B, if it has an atmosphere at all, would be driven by the permanent day-night divide. Hot air would rise on the day side and flow toward the night side, where it would cool and descend. A perpetual circulation pattern would result, with fierce winds flowing around the planet's terminator, the boundary between day and night. The night side might be so cold that whatever atmosphere the planet has would freeze out, forming glaciers of nitrogen and carbon dioxide. Or perhaps the circulation would keep temperatures moderated, distributing heat more evenly across the surface. The flares from Proxima Centauri would be visible events, sudden brightening of the already dim red Sun. During major flares, the star might increase in brightness by a factor of 10 or more, briefly bathing the planet in harsh ultraviolet light. Any life on the surface would need protection from these events, perhaps sheltering underground or in caves or beneath several meters of water. The rhythm of flares would be unpredictable, a constant danger lurking in an already hostile environment, and yet life is remarkably adaptable. On Earth, we have found organisms that thrive in environments we once thought were completely sterile. Hot springs, frozen wastes, deep ocean trenches, the pores inside rocks. Anywhere there is a source of energy and the basic chemistry of carbon and water, life seems to find a way. Perhaps Proxima B, for all its challenges, could support its own unique biosphere. Perhaps strange creatures have evolved there, adapted to conditions we can barely imagine. This is one of the great unanswered questions in science. How common is life in the universe? Does it arise easily whenever conditions are even marginally suitable? Or is it a rare and precious phenomenon requiring a very specific set of circumstances that may exist nowhere else? We do not know. The only way to find out is to look, to explore, to test our theories against reality. And Alpha Centauri, as our nearest neighbor, is where we must begin. Now let us contemplate time. The light you see when you look at Alpha Centauri left those stars about 4 years ago. The events you observe are not happening now, but have already happened, their light only now reaching your eyes across the vast distance. In a sense, astronomy is always archaeology. We are studying the past examining light that has traveled for years or centuries or billions of years before arriving at our telescopes. When the James Webb Space Telescope observed Alpha Centauri A in August of 2024, it was seeing the star as it existed in August of 2020. Any planet detected in that observation was being seen in its position from 4 years earlier. By the time the data was analyzed and the discovery announced, the actual positions of everything in the system had changed. The planet, if it exists, had continued its orbit, the stars had continued their dance, and time had continued its relentless forward march. This delay imposed by the speed of light is fundamental. It cannot be overcome. No matter how advanced our technology becomes, we will never be able to see distant objects in real time. The universe insists on showing us the past. Even something as close as Alpha Centauri presents us with a 4-year delay. The nearest large galaxy, Andromeda, is seen as it was 2.5 million years ago. The most distant galaxies visible to our telescopes are seen as they were billions of years ago, in the infancy of the cosmos. There is something profound in this. We live in a universe where the past is visible, but the present is hidden, where light carries history across the void, but never manages to arrive instantly. The speed of light is fast but finite, and that finitude shapes our experience of reality in fundamental ways. This also means that any message we send to Alpha Centauri would take 4 years to arrive, and any response would take another 4 years to return. A conversation between Earth and a hypothetical civilization at Alpha Centauri would be agonizingly slow, each exchange taking nearly a decade. Patience would be essential. Misunderstandings would be costly. And yet, such a conversation would be the most significant event in human history. Imagine receiving a signal from Alpha Centauri, an unmistakably artificial transmission, proof that intelligence exists elsewhere in the universe. The world would be transformed. Every religion, every philosophy, every political system would have to grapple with the implications. We would no longer be alone. The universe would suddenly seem much more crowded, much more interesting, much more meaningful. Or imagine detecting biosignatures in the atmosphere of a planet around Alpha Centauri. Not intelligence, just life. Simple organisms perhaps, bacteria or algae, or something with no earthly analogue. Even this would be revolutionary. It would prove that life arises independently, that the chemistry that led to us is not unique to Earth. It would suggest that life might be common throughout the cosmos, even if intelligent life is rare. These possibilities hover in our future, tantalizing and uncertain. We do not know what we will find when we explore Alpha Centauri in detail. We do not know what the next generation of telescopes will reveal. We do not know whether the search for life will succeed or fail. But we keep searching, because that is who we are. Curious, persistent, unwilling to accept ignorance when knowledge might be attained. The night grows deeper now, and perhaps your eyelids are growing heavy. The journey we have taken together has covered vast distances and grappled with profound questions. Let us now begin to bring this voyage to a close, spiraling gently back to Earth, back to the present moment, back to the simple comfort of rest. The Alpha Centauri system will continue to shine, regardless of whether anyone is watching. The 3 stars will continue their ancient dance, orbiting and whirling and burning hydrogen, indifferent to the tiny creatures on a distant planet who point telescopes in their direction. Any planets that orbit those stars will continue their own journeys, winter following winter in cycles that have repeated billions of times and will repeat billions more. And here on Earth, astronomers will continue their work. They will analyze data, write papers, build new instruments, propose new observations. They will argue about interpretations, challenge each other's assumptions, and gradually, collectively, move us closer to understanding. Science does not sleep. Even as you drift off, someone somewhere is at a telescope, gathering photons, peering into the cosmos, pushing back the boundaries of the known. The James Webb Space Telescope continues its silent vigil, floating in the darkness beyond the moon. Its golden mirrors are still collecting light from across the universe. Its instruments are still converting that light into data. Somewhere in that data stream are secrets we have not yet discovered, revelations we have not yet experienced. The universe is constantly sending us messages, and we are slowly learning how to read them. What will we learn about Alpha Centauri in the coming years? Will the candidate planet be confirmed? Will new planets be discovered? Will we find signs of habitability or even life? These questions cannot be answered tonight. They require time, observation, analysis, and patience. But they will be answered eventually. Human curiosity is relentless. Our tools grow sharper with each generation. Someday, perhaps sooner than we expect, we will know the Alpha Centauri system, as well as we know our own solar neighborhood. And beyond Alpha Centauri, the galaxy stretches out in all directions, hundreds of billions of stars scattered across 100,000 light-years of space. Each of those stars might host planets. Many of those planets might harbor life. The opportunities for exploration are essentially infinite, limited only by our imagination, our resources, and our lifespan as a species. We are at the very beginning of this journey. Humanity's exploration of the cosmos is in its infancy. We have barely begun to explore our own solar system, let alone the vast gulfs beyond. But beginnings are important. Every great journey starts with a single step, and we are taking those first steps now. The observations of Alpha Centauri, the development of interstellar probe concepts, the search for biosignatures and technosignatures. These are the first faltering steps of an infant species, learning to walk among the stars. Perhaps someday, far in the future, our descendants will look back on this era with the same affection we feel for the first human explorers who ventured beyond the savannas of Africa. They were our ancestors, the pioneers who took the risks and made the discoveries that eventually led to us. And we are the ancestors of those future star voyagers, the generation that built the telescopes and analyzed the data and dreamed the dreams that will eventually carry humanity to other worlds. This is our role in the cosmic story. We are the bridge between the earthbound past and the spacefaring future. We are the ones who first saw planets around other stars, first seriously planned missions to other star systems, first grappled with what it means to be one species among potentially many in a galaxy teeming with life. Our great-grandchildren will inherit the consequences of what we do now, for better or worse. Let this thought accompany you into sleep. You are part of something larger than yourself. Your existence matters, not just for what you accomplish individually, but for what humanity accomplishes collectively. And humanity is accomplishing remarkable things. We are reaching out to the stars. We are asking the deepest questions. We are seeking our place in the cosmic order. Now let me return once more to the science, to the tangible facts that anchor all our speculation and wonder. Let us consider what makes Alpha Centauri A such an excellent target for the search for habitable worlds, and what the discovery of a giant planet there means for that search. Alpha Centauri A is what astronomers call a solar analog. Its surface temperature is nearly identical to our Sun's, around 5,790 degrees. Its mass is just 10% greater. Its age is roughly the same, about 5 billion years. If you were designing a star system most likely to produce conditions similar to Earth, Alpha Centauri A would be an excellent choice. The habitable zone around Alpha Centauri A, the region where a planet could have liquid water on its surface, is slightly further from the star than Earth's orbit around our Sun. This is because Alpha Centauri A is slightly more luminous. A planet receiving the same amount of energy as Earth receives from our Sun would need to orbit at about 1.2 to 1.3 astronomical units from Alpha Centauri A. Such a planet would have year lengths of about 1.4 Earth years and would experience seasons if it had a tilted axis. The candidate giant planet discovered by Webb orbits at about 1 to 2 astronomical units from Alpha Centauri A, depending on where it is in its elliptical path. This means it passes through the habitable zone during its orbit. While the giant planet itself could not support life as we know it, lacking a solid surface, its presence has interesting implications. First, the fact that a giant planet can exist and maintain a stable orbit in a binary star system tells us something important. The gravitational influence of Alpha Centauri B, lurking some 11 to 36 astronomical units away, does not prevent planet formation around Alpha Centauri A. This was not a foregone conclusion. Some theories suggested that binary stars with separations as small as Alpha Centauris would disrupt any forming planetary systems, scattering planetesimals before they could accrete into mature worlds. The existence of a giant planet challenges these more pessimistic models. Second, a giant planet at this distance could have influenced the delivery of water and organic materials to any inner planets that might exist. In our solar system, Jupiter is thought to have played a crucial role in the early bombardment that brought water to Earth. Giant planets scatter comets and asteroids, some of which impact inner worlds, potentially delivering the volatile compounds necessary for life. A similar process might have occurred in the Alpha Centauri A system. Third, as we have discussed, giant planets often have moons. Saturn has more than 140 known moons. Jupiter has nearly 100. If the candidate planet around Alpha Centauri A is anything like our solar system's giants, it might host its own collection of moons. Some of these could be large enough to have their own geologic activity. Some might have subsurface oceans, heated by tidal forces from their parent planet. In our solar system, moons like Europa and Enceladus are considered prime targets in the search for life. Similar moons around Alpha Centauri might be equally promising. The possibility of habitable moons is fascinating because it greatly expands the potential real estate for life in the universe. Planets in habitable zones are relatively rare, limited to narrow orbital bands around their stars. But moons can exist throughout a planetary system, heated not by starlight but by tidal forces, radioactive decay, or gravitational interactions. If life can arise on such moons, then habitable environments might be far more common than we currently estimate. This brings us to a concept that has captured the imagination of astrobiologists in recent years. The concept of habitability is not as simple as just being the right distance from a star. A world needs the right chemistry, the right geology, the right atmospheric composition. It needs a source of energy and protection from harmful radiation. It needs stability over long timescales. All these factors must come together for life to arise and persist. Earth exemplifies this fortunate combination. Our planet sits in the habitable zone of a stable G-type star. We have a large moon that stabilizes our axial tilt. We have a strong magnetic field that deflects solar wind and cosmic rays. We have plate tectonics that cycle carbon and regulate our climate. We have abundant liquid water and a rich supply of organic chemistry. All these factors, working together, created conditions where life could emerge about 4 billion years ago and has flourished ever since. How many of these factors are essential? How many are merely helpful? Could life arise on a world lacking one or more of Earth's advantages? We do not know. Earth is the only example we have. But studying other planetary systems, including Alpha Centauri, helps us understand which factors are truly necessary and which are optional extras. Each discovery narrows the possibilities, guiding our search for life elsewhere. The red dwarf problem illustrates this nicely. Proxima Centauri is a red dwarf, a type of star that is by far the most common in the galaxy. More than 70% of all stars are red dwarfs. If planets around red dwarfs are habitable, then habitable worlds might be extraordinarily common. But if red dwarf flares and tidal locking make such planets unsuitable for life, then we need to focus on the much rarer Sun-like stars. The evidence remains mixed. Proxima Centauri's frequent flares are concerning. The tidal locking of Proxima B raises questions about atmospheric stability and climate. But some studies suggest that thick enough atmospheres could protect against both problems. Some theories propose that life might thrive underground, sheltered from surface radiation. The debate continues, and observations from Webb and future telescopes may eventually resolve it. Meanwhile, the Sun-like stars Alpha Centauri A and B offer a different kind of opportunity. These stars are much calmer than Proxima Centauri. Their habitable zones are far enough away that planets there would not be tidally locked. Conditions on such planets might be much more Earth-like than anything around Proxima. If we find rocky planets in the habitable zones of Alpha Centauri A or B, they would be prime targets for the search for life. The search for such planets is ongoing. The direct imaging approach used by Webb is one technique, but there are others. The radial velocity method, which detected Proxima B, could potentially find planets around Alpha Centauri A or B if they are massive enough and close enough to induce measurable stellar wobble. The transit method is unlikely to work for this system because the geometry is unfavorable, but it cannot be completely ruled out. A technique called astrometry, which measures the tiny side-to-side wobble of a star caused by orbiting planets, is being developed by the European Space Agency's Gaia mission. Gaia is mapping the positions and motions of more than 1 billion stars with unprecedented precision. Over time, this data might reveal the gravitational influence of planets around nearby stars, including Alpha Centauri. The results are still being analyzed, with major data releases expected in the coming years. All these techniques are complementary. Each has strengths and weaknesses. Each is sensitive to different types of planets in different types of orbits. By combining multiple approaches, astronomers can build a comprehensive picture of what kinds of worlds exist around nearby stars. The more tools we have, the better our chances of discovering something remarkable. Let me now take you on one more imaginative journey. Picture yourself aboard a spacecraft approaching the Alpha Centauri system after a 20-year voyage. You have crossed the void between stars, traveling at a significant fraction of the speed of light. Now the 3 stars of Alpha Centauri grow brighter ahead, no longer pinpoints, but distinct suns, each casting its own light through the windows of your craft. As you decelerate, Assuming your spacecraft has that capability, the system slowly reveals itself. Alpha Centauri A blazes yellow-white, familiar and welcoming, so much like the sun you left behind. Alpha Centauri B glows with an orange warmth, its cooler surface creating a different quality of light. And there, in the distance, barely visible even now, Proxima Centauri glimmers red, its feeble output a reminder that not all stars burn as brightly as the ones that dominate our sky. Your instruments begin to pick up details. The candidate planet around Alpha Centauri A resolves from a single point of light into a disk. Bands of clouds become visible, swirling patterns of atmospheric circulation driven by the star's heat. Perhaps rings encircle the planet, catching the light and glittering like a halo. Perhaps moons dot the space around it, each a world unto itself, each potentially harboring its own secrets. You adjust your trajectory, angling toward the planet for a closer look. As you approach, the scale becomes apparent. This is a world larger than Earth, larger than Neptune, perhaps approaching Jupiter in mass, though smaller in size. Its atmosphere is thick and turbulent, storms the size of continents churning beneath you. Lightning flashes in the clouds, brief sparks illuminating vast depths of gas and vapor. You scan for moons, and your sensors find them. Dozens of small irregular bodies, captured asteroids perhaps, tumbling chaotically in distant orbits, but also larger moons, spherical worlds with their own gravitational pull, their own geology, their own potential for wonder. One shows a smooth, icy surface, possibly concealing an ocean beneath. Another has a thin atmosphere, a haze of gases clinging to a rocky surface. Each deserves investigation. Each might hold answers to questions we have asked for centuries. But your mission is brief. Your spacecraft cannot linger. The vast energies required to reach this speed cannot be easily shed. You are passing through a momentary visitor, gathering what data you can before continuing into the galaxy beyond. Your cameras capture images that will be studied for decades. Your spectrometers analyze light that will reveal chemical compositions. Your radio dish transmits everything back toward Earth, where eager scientists wait to receive news from humanity's first interstellar explorer. And then Alpha Centauri is behind you, shrinking in your rear view, returning to the appearance of ordinary stars. Ahead lies the galaxy, hundreds of billions of stars spread across 100,000 light years, each potentially hosting worlds, each a possible destination for some future voyage. Your journey has only begun. This is the future that awaits us if we continue to explore, continue to develop new technologies, continue to reach beyond our current limitations. It is not guaranteed. Many challenges lie between here and there, but it is possible, and the discoveries being made now with Webb and other instruments are the foundation on which that future will be built. As we draw closer to the end of our journey together tonight, let us return to the present moment and reflect on what we have learned. The James Webb Space Telescope has observed the Alpha Centauri system and found evidence of a possible Saturn-mass planet orbiting Alpha Centauri A. This candidate planet, if confirmed, would be the closest world ever directly imaged around a sun-like star. It would orbit in a path that carries it through the habitable zone. Though as a gas giant, it is unlikely to support life itself. Its moons, however, might be another story. The search for planets around Alpha Centauri continues. Proxima Centauri has at least 2 confirmed planets, including the Earth-sized Proxima B in the habitable zone, though the habitability of that world is questionable due to stellar flares. Alpha Centauri B has no confirmed planets yet, despite earlier false alarms. The gravitational complexity of this triple star system creates both challenges and opportunities for planet formation and survival. Looking ahead, new telescopes and missions will continue the exploration. The Nancy Grace Roman Space Telescope, the Extremely Large Telescope, and future missions not yet conceived will push the boundaries of what we can observe. Perhaps within our lifetimes, we will know definitively whether planets like Earth exist around our nearest stellar neighbors. Perhaps we will even find signs of life. And in the longer term, projects like Breakthrough Starshot offer the tantalizing possibility of actually visiting these worlds, at least with robotic probes. The challenges are immense, but so is the human drive to explore. We have always been restless wanderers, pushing beyond the next horizon, climbing the next mountain, crossing the next ocean. The stars are simply the next frontier. Now, as the night deepens and sleep beckons, let us slow down. Let us breathe. Let the vastness of space become not overwhelming, but comforting. The universe is large, yes, incomprehensibly large, but it is also beautiful. It is ordered by elegant physical laws. It produces wonders that beggar imagination, and we are part of it. The stars that shine above us tonight are the same stars that have shone for billions of years. They will continue shining long after we are gone. There is permanence in the cosmos, stability amid the seeming chaos. Galaxies rotate slowly. Stars burn steadily. Planets trace their predictable paths. The universe is not random. It is structured, patterned, comprehensible. And the fact that we can comprehend it is itself a wonder. When you look up at the night sky, you are seeing the same stars that your ancestors saw. The same Alpha Centauri that shines tonight shone over the pyramids of Egypt. It shone over the philosophers of ancient Greece. It shone over every human being who ever lived and looked upward with wonder. That star has been our constant companion through all of human history, a beacon in the darkness, a promise of worlds beyond our own. And now, for the first time, we are beginning to learn what secrets that stellar neighbor holds. We are detecting planets, characterizing orbits, measuring temperatures and compositions. We are transforming Alpha Centauri from a point of light into a place, a destination, a set of worlds with their own stories and their own mysteries. This transformation is one of the great gifts of science. It takes the unknown and makes it known. It takes the fearsome and makes it familiar. It takes the impossibly distant and brings it within reach, if not of our bodies, then at least of our understanding. The universe becomes less alien and more like home with every discovery we make. So as you drift off to sleep tonight, carry with you this thought. Somewhere out there, just 4 light years away, 3 stars are shining. Around at least one of those stars, planets may orbit. On at least one of those planets, conditions might exist that could support life. And even if life is not there, even if those worlds are sterile and empty, they are still remarkable. They are still part of the same cosmos that produced us. They are still connected to us by the fundamental forces of nature, the shared chemistry of the universe, the common origin in the Big Bang that started everything. The light from Alpha Centauri that reaches your eyes tonight began its journey before some of you were born. Think about that. Those photons left their source years ago, traveled across trillions of miles of emptiness, and finally ended their journey by being absorbed by the cells in your retina. You are connected to Alpha Centauri by light itself. You are participating in a cosmic exchange that has been going on since stars first began to shine. Let this connection comfort you. You are not alone in the universe. Even if we never find other life, we have each other. We have the bond of shared existence, the kinship of consciousness, the miracle of awareness arising from the dust of dead stars. And we have the stars themselves, eternal beacons in the night, reminding us that there is more to existence than our daily concerns, more to reality than what we can touch and hold. The Alpha Centauri system will be there when you wake up tomorrow. It will be there next week and next month and next year. It will be there when your children grow old and when their children have children of their own. The stars endure. They are patient. They wait for us to come to them in our own time, at our own pace. And we will come. Perhaps not in your lifetime, perhaps not in your grandchildren's lifetimes, but someday humanity will reach the stars. Someday ships bearing human beings or their robotic emissaries will cross the void to Alpha Centauri. Someday the light from our civilization will shine back from those distant worlds, a testament to the restless spirit that drove us ever outward, ever upward, ever toward the unknown. That future is being built right now. Every observation with the James Webb Space Telescope contributes to it. Every scientist analyzing data, every engineer designing instruments, every dreamer imagining possibilities plays a role. And you too play a role, simply by caring, simply by wondering, simply by looking up at the stars and asking what is out there. The universe rewards curiosity. It reveals its secrets to those who seek them. It opens its vastness to those willing to look. And tonight, as you close your eyes and let sleep take you, know that the cosmos is still out there waiting to be explored, waiting to be understood, waiting for you to wake up tomorrow and continue the great human adventure of discovery. Let your breathing slow now. Let your muscles relax. Let your thoughts drift like stars across the vast dark sea of space. You have traveled far tonight, from Earth to Alpha Centauri and back again, crossing light years with your imagination, touching worlds that no human hand has ever touched. It is time now to rest. The stars will watch over you as you sleep. They have watched over every sleeping human since the dawn of our species. They ask nothing in return. They simply shine, pouring their light into the void, illuminating the darkness, offering their warmth to any world lucky enough to bask in their glow. Alpha Centauri is shining right now. Perhaps clouds of gas drift around its stars, remnants of planetary formation or stellar wind. Perhaps planets orbit there bathed in yellow and orange light, their surfaces sculpted by forces we understand, because they are the same forces that shaped our Earth. Perhaps, somewhere in that system, conditions exist that we would recognize as comfortable, even familiar. We do not know yet. That is the beauty of exploration. There is always more to learn, always another horizon to cross, always another mystery to solve. The unknown is not something to fear. It is something to embrace. It is the frontier where all great discoveries are made. So sleep well tonight. Dream of stars and planets, of rockets and telescopes, of light crossing the void and secrets waiting to be revealed. Dream of a future where humanity is spread to the stars, where Alpha Centauri is not just a destination, but a home. Dream of the wonders that await us, just 4 light years away, shining patiently in the darkness. The universe is vast and old and mostly silent, but within that vast silence, something remarkable has happened. Matter has organized itself into forms that can wonder about their own existence. Energy has found pathways into consciousness. The cosmos has produced beings capable of looking back at it and asking why. You are one of those beings. You are the universe wondering about itself. And the universe appreciates your curiosity. It rewards it with beauty, with mystery, with the endless joy of discovery. Tonight you learned about Alpha Centauri. Tomorrow you will learn about something else. The journey never ends. Good night, cosmic traveler. The stars will be there when you wake up. Alpha Centauri will still be shining. The James Webb Space Telescope will still be gathering light. The search for planets and life will continue. And you will continue too. Another day in the grand adventure of existence. Another chance to wonder at the majesty of the cosmos. Sleep now. Rest. Dream of distant suns and undiscovered worlds. And when you wake, remember that you are made of stars, connected to everything in the universe by physics and chemistry and the simple fact of existence. You belong here. You are part of this. And the universe is glad that you took the time to look up and wonder. The night grows quiet. The stars shine on. And somewhere, just 4 light years away, 3 stellar companions continue their eternal dance, keeping secrets that we are only now beginning to uncover. What will we find there? What wonders await? Only time will tell. But for now, it is enough to know that they are there, that our nearest stellar neighbors host mysteries worth solving, that the universe is bigger and more interesting than we ever imagined. That is enough for tonight. That is enough to carry us into dreams. Rest well. The cosmos holds you. The stars watch over you, and tomorrow the adventure continues.